Our next panel, really important, kind of looking at the Mars science precursors and the international component to those and how they can advance us getting to Mars, hopefully in the 2030s. And of course, leading this panel is somebody I think you probably all know, Dr. Jim Green. If I gave his full biography, we'd probably have to bump all the rest of the speakers for the rest of the day just to get through it. But you probably know him well as, you know, a former chief scientist at NASA. He was a former head of planetary science. And of course, Jim has been a long-time participant in the Humans to Mars Summit. I think you participated probably in the first one back in 2013 as well. And probably our first conference back in 2011 as well. So long-time participant with Explore Mars. So, Jim?
Thank you so very much, Chris. So we talk a lot about humans to Mars, but there's all these scientific precursors that have to go. I mean, we have to be able to know everything about Mars to buy down the risk that allows human exploration to be successful. So our panel, the active members in the scientific community, the managers of these major missions from 3 major agencies are here, and we're going to go through what's happening and what their next steps are. So let me introduce Dr. Lori Glaze. Lori, come on out. Lori is the Division Director of Planetary Science at NASA headquarters. Next, from the European Space Agency, is Albert Haldemann. Albert, please come out. So let me get your title right. Albert is the Mars Chief Engineer in the Mars Exploration Group. So his group also contains astronauts that talk a lot about going to the moon and then on to Mars. So it's a perfect interaction that you guys have. And then finally, from the Japanese Space Agency, once again, we'll have Dr. Masaki Fujimoto. Masaki, please come. All right, please take a seat. So to begin this, let's talk about what the 3 agencies are really doing in the science area and how they're really developing not only a science strategy, but how that relates to human exploration. So let me go to Lori first.
All right.
What's the Mars Exploration Group up to?
Thanks, Jim. First, I just want to say it's so great to be back here at Humans to Mars. This is always a great meeting, and it's always fun to get to be a part of it. It's also great to be up here on the panel with Albert and Masaki, and great to hear about all the wonderful things we're doing. Of course, in NASA's program, we really enjoy and get a lot of benefit from our collaborations with our international partners, in particular with European Space Agency and with JAXA. With ESA, we've already got missions already operating around Mars that you're probably familiar with Mars Express and with the Trace Gas Orbiter. We're looking forward to working and partnering with ESA on the Rosalind Franklin rover, which is coming up, and I'm sure Albert will probably talk to that a little bit more. With the Japanese Space Agency, of course, we're working closely on the Mars Moon Explorer, which I'm sure Masaki will speak to, so I don't want to steal their thunder. But I did want to spend a few minutes talking about the Mars Perseverance rover and Mars sample return. And I think, if we're lucky, there might be a video. Fingers crossed, we'll see if we can get it to load up. Can we cue the video on the monitor? We'll see. So as most of you are probably aware, right now we have the Perseverance rover, which is exploring within Jezero crater on Mars. Jezero was chosen specifically because it's a great location to not only do science, geology, and understanding the age of the crater. We're collecting rocks of lava from the base of the crater that can help us age the crater itself. We can also understand the environment on Mars 3.5 billion years ago, what that was like. But also what makes it particularly unique is that there's a river delta that runs, a river that ran into the crater, depositing a river delta, which could have 3.5 billion years ago been a place where evidence of life could have been preserved. We're with Perseverance, of course. We're already collecting samples on Mars, and with the intent of bringing these samples back with Mars sample return. So you can see here Perseverance sitting in Jezero crater and looking up into the sky as the sample retrieval lander lands onto the surface of Mars. The lander, of course, is going to be provided by NASA with participation from ESA that provides the robotic arm that's going to transfer those samples as Perseverance delivers them to the lander. They get delivered into a sampling container there that's going to hold all of those samples, up to 30 samples that can be returned back to Earth. And then we are going to do something amazing here. We are going to load those into the Mars Ascent vehicle, and this part always makes me nervous. But that's what we're going to do. We're going to launch that rocket from the surface of Mars, the first time ever launching a rocket from another planet. We're going to release the samples in that orbiting sample container and release those into orbit around Mars to be collected, captured by the European Space Agency Earth Return Orbiter that's carrying the capture containment system that's being built at Goddard Space Flight Center. It's going to capture those samples, contain them within the entry system, and then the orbiter will return back to Earth and release the samples to land in the Utah desert, where we can then take those samples and study them with instruments that we don't even have yet, that we don't even know what they are. We're using techniques that we haven't developed yet, and scientists that are probably in elementary school right now. And so this is going to be a fantastic endeavor to collect these samples to help us learn, as I said, about the geology, the chronologic history of Mars, but also the history of potential past life on Mars. Incredibly complex mission. I feel certain we're going to talk about this a lot more, so I don't want to spend too much time talking about Mars sample return right now. But I think there's a lot of feed forward. A lot of the complexities of the Mars sample return mission are going to help us to buy down some risk as we start to plan for human exploration of Mars. I wanted to speak a little bit also about some of the things in the future for the Mars exploration program at NASA. Some of you may know that just a little over a year ago, the National Academies provided a decadal survey for planetary science and astrobiology. There are a lot of recommendations in that study for science, priority science to be done within all of planetary science, but in particular for Mars. One of the big missions that they recommended in that decadal survey is something they called the Mars Life Explorer. This would be the next mission beyond Mars sample return, and really an attempt to really go looking for potential biosignatures on the surface of Mars. So that's an ambitious mission. It's intended to be not a huge mission. It's intended to be a medium-class mission, but still the scientific goals are pretty ambitious. Another part of that decadal survey also recommended that NASA's Planetary Science Division put together a plan for the Mars exploration program, a strategy, if you will, going forward after Mars sample return. And I think this is really important because the Mars exploration program is kind of at an inflection point right now. We've had a goal for getting to Mars sample return for a long time. We're achieving that goal. But we're also seeing more capabilities and interests across the international community, within the commercial sector. And so I think we have an opportunity to kind of change our paradigm for how we explore Mars, with a focus on more frequent, smaller missions that can continue our science. Within that plan, we actually have a draft of that plan out right now that's available for community comment. So we're continuing to iterate and build on what that plan will be. There's a strong focus in that plan on trying to make sure we have sustained infrastructure at Mars. So that includes communications, but it also includes high-resolution imaging. We want to be able to replace the high-resolution imaging that we have now, the capability we have now, as we plan particularly for human exploration to make sure we're able to identify potential landing sites and really characterize those scientifically before we go. There's also an emphasis on preparing, as I said, for human exploration as part of that, but also science. And then finally, as I said, making sure we're taking advantage of international partnerships and commercial capabilities. And in that sense, not just our traditional partners, which are great, but also looking for emerging interests from countries that are just beginning to think about how they can explore the solar system. The last thing I really wanted to chat about just briefly before I hand things over to Albert is just, again, thinking about NASA's plans for human exploration of Mars. I know you're going to have a panel here tomorrow with the three big AAs, the three big associate administrators, with Nikki Fox and Jim Free and Jim Reuter going to be here to talk about the plans for NASA's human presence on Mars. But what's really important, and you'll hear a lot more about it tomorrow, is that as they're rolling out, as the new organization within the human side of NASA now includes explicit organizations focused on what are we going to do when we get to Mars, and science is in that conversation. I think that's incredibly important. We have science on the ground floor in those conversations, and I'm sure that you're going to hear from Nikki Fox tomorrow about the importance of making sure that science is driving what we do with the human exploration on the NASA side. So with that, I think I'll
Okay, that's
wrap
great.
up.
You know, if we can bring Mark Watney home, we ought to be able to bring those 30 samples back.
Exactly.
So that'll be extremely important. And of course, science that we're doing on Mars, and also what we want to do on the moon, we want to continually raise our voice and be heard and be part of the next endeavor. All right, Albert, what's happening?
Thank you, Laurie. What's happening at ESA? And I'll say at the outset, I'm Swiss, but I sound like I do because my mom's from Wyoming. So ESA has an exploration program, and happily we decided to modify the name into something a little bit more ambitious, Terra Nove, new lands, new worlds. It was called the European Exploration Envelope Program, E3P, very engineering oriented, not very motivational, but that's an important part of what we want to do with exploration. Inspire, and I'll go to my next slide because it kind of says that. Maybe. There we go. We have 4 elements to our exploration program, and I'll take a little credit at ESA that this was endorsed by our stakeholders in 2014 as an exploration program structure. Knowledge, science drives why we explore. At ESA, we don't do very much in-house. 85% of our budget is directly spent into industry. That is a major distinction with how the European Space Agency functions. So we're interested in continuing that. So economy, innovation, technology development is another pillar of how and why we do exploration. Of course, we want to inspire the next generations and the people doing the work for that matter. InReach is really important for people to be motivated to do those other things, the science and the economy. And then, of course, being the European Space Agency is not a national space agency, it's a multinational space agency. It's a treaty-based international organization, like the International Labour Organization or WHO. We have 22 member states, we have 4 associate member states, Canada is a cooperating state, so we already do cooperation just to keep ourselves working together, but I think it's something we're good at, and we partner with other agencies across the world, around the globe. And it's also an element of our objectives for our exploration program that we do that and that we lead in doing that. The implementation elements of our exploration program is based on 3 destinations, which we partition into 4 cornerstones. There is humans in low Earth orbit, there is humans beyond low Earth orbit heading to the moon with the Artemis program, and robotic exploration at the moon in support of Artemis and in support of exploring beyond cislunar space, and then there is Mars robotic exploration. That's where we are implementing now. As Jim alluded to, I work in the Directorate of Human and Robotic Exploration. So within ESA, that directorate does astronauts, robots to the moon and Mars, space station, and is bracketed by, in this diagram, the technology developments, that's the expert program, the science that we implement in human physiology, as well as other experiments in low Earth orbit and cislunar space, space. And even though we put 85% of our budget into our industry anyway, we are in some sense a commercialization organization to that extent. We're looking at new ways to implement that commercialization in family with the new space ambitions around the world and taking note of how things are moving in other parts of the world, the US in particular, to remain a relevant partner overall. So then finally, this is where we are now. Speaking to the right-hand side of the screen and what we're doing at Mars, we have currently the Trace Gas Orbiter, which has been in space since 2016 and is functioning well. It is taking images, but it has delivered some answers and some additional questions to the curious scientific question of where's the methane? There were Earth-based observations of methane, not quite convincing. Then we had a science objective to send trace gas detection into Mars orbit. In the meantime, at the surface, Curiosity found methane. We were sending trace gas orbiter to map the methane all over the planet, except it hasn't seen any. So that also is a discovery, because Curiosity's discovery is correct. It's been verified and validated, and so is ours in orbit. We need to explain that, and that was an unexpected result. Mars threw us a curveball. And that's the kind of stuff we need as a basis to really understand what is different about Mars. We're going there to get samples. That's going to anchor a lot of understanding of planetary evolution with the Earth return orbiter contributing to the Mars sample return, and the sample transfer arm on the sample retrieval lander. People know about the Canadarm. People know about the robotic arms on the Mars landers that NASA has worked on. Unfortunately, it took a long time for the European robotic arm to get delivered to the International Space Station, but there's some videos on YouTube right now that are demonstrating our robotic arm capability on the Russian module, moving radiators around. It's now operational and working well. And it's that know-how that we're applying to the sample transfer arm in cooperation with the team at JPL who are building the sample retrieval lander. So that's investing in the Mars sample return, and the long storied, difficult history of the Rosalind Franklin rover is a critical element in building towards our understanding of science on Mars. We're not going to bring the samples that Rosalind Franklin takes back to Earth, but they are going to be acquired in the deeper subsurface than those that we will bring back to Earth. The 2-meter drill will be, I shouldn't say Earth-breaking, it'll be Mars-breaking. Going down as deep as 2 meters, but that is below the level of cosmic ray influence on superficial materials. It's probably also below the level of the oxidation that's caused by perchlorates in the Martian soil. Both of those things should aid preservation of the samples. And on board, we have the Mars Organic Molecule Analyzer, a German-French US collaboration instrument, and it will do groundbreaking organic analysis on Mars. We know from Curiosity and Perseverance there are organic molecules there, and we're going to go look at what they're like 1.5 meters, 2 meters down, and do that in situ. All of that is sort of how we're building towards the future where science, from that initial basis, science leads our exploration program in cooperation with other agencies, and in some cases taking a leading role, like ExoMars. Thank you.
All right, fantastic. Masaki, you had talked a little bit about the JAXA program at the Moon and Mars. Perhaps you can elaborate on some of the fantastic things that JAXA is doing.
Right, thank you. So, Masaki Fujimoto from JAXA, the Science Institute of the Space Agency. So this is the MMX, Mars Exploration, I forgot the name, it's MMX, Martian Moons Exploration. Yes, so it will return samples back from Phobos, one of the Martian moons. So this is our first step in the Mars exploration, JAXA's first step in Mars exploration. But what do we do beyond this? So this is the Moon and Mars program. So there's a direct contribution to Artemis, like a manned mission, but in addition to those big programs, we try to have smaller programs driven by science. So we will try to have smaller programs on the surface of the Moon, and then that should have some feed into our Mars landing program. That's what this diagram is showing. So what I mean by JAXA's Mars landing program, it's going to happen in 3 steps, and then there will be a feed from the lunar exploration. And at the same time, we try to take this, establishing this Mars landing program to change the way we do the deep space exploration. So in this program, we try to establish the kind of common asset for deep space exploration, or orbit transfer vehicle, OTV. So after the first step of this Mars landing program, we will try to send all the deep space exploration by the common orbit transfer vehicle. And that way we can lower the hurdle for deep space exploration into the future, and we can have our program in a more efficient way. So it's this Mars landing program is not just for enabling Mars landing, but it's also for changing the way we do the deep space exploration in the future. How do I think I have a chance of establishing this Mars landing program? We don't need to do what NASA has done in the past, but at a miserably smaller scale. We will try to do alternative. We try to establish an alternative way of landing or exploring the surface of Mars. And how do I think I have a chance? Because it has relevance to our engineering expertise. We have managed to, is the movie working? I don't know how to start the movie, so can you? So we have made this very nice sample return capsule recovery successfully in the desert of Umera. So we do have some relevance we do have some engineering expertise in this entry capsule. And here. And then in the Martian atmosphere, if you think about the Martian environment, the Martian atmosphere is really tenuous. And because it's tenuous, you don't have to worry so much about the heat during the descent. But and if you're interested only in bringing smaller mass, if you're interested in lightweight access to the surface of Mars, you can have an alternative technology for EDL, for the entry, descent, and landing. And actually, that's the inflatable soft aeroshell. In a tenuous Martian atmosphere, you don't have to worry too much about the heat, but you better worry about decelerating your asset to the ground. So you better have a bigger area exposed to the atmosphere. And that's what you can do with an inflatable soft aeroshell. And we have been developing this technology, so we have some expertise. And with this, we think we can bring something like 200 kilogram-ish rover to the surface of Mars. And our scientists say that we can do a great deal of science with that kind of rover. And that's what I mean by OK-sized asset on the surface of Mars. And maybe we can have this mission more frequently if we team up with our international partners. So that's the concept we have. And we are kind of developing the plan so that we might be able to fly the first tech demonstration within the next several years or something like this. So take-home message is that scientists and engineering teaming up under the limited resources. That's our way, JAXA IDA's way. And we are interested in lightweight access to the surface of Mars because even if it's lightweight, we can do a lot, especially if we do this frequently. And we have an idea to do it in a shareable form. So we'll be happy to establish a new way of exploring the surface of Mars in partnership with smaller countries. A small country means that who has interest in Mars exploration but doesn't have the capability to package the whole program. And I will be happy to partner with those newcomers in a sense. So yeah, we're really interested in a frequent OK-sized mission to the surface of Mars. That's all I have to say. Thank you.
Okay, wonderful. Well, as you can see, each of the agencies have enormous efforts going on in major scientific achievements that are being planned. But many of those achievements are actually going to, what we call, feed forward into the human exploration activities that are going to follow on. So as a general question to each, Lori, what do you think some of the major things that will be discovered through the sample return, ice mapper, et cetera, that are all precursors that will be important for human exploration?
Yeah, so I think let's talk science first, right? So you mentioned Mars Ice Mapper, which we haven't really discussed here yet today, but the Ice Mapper is a really, I think, interesting multinational collaboration primarily between Canada and JAXA and Italian Space Agency, and with NASA also hoping to participate as well. We've been engaged in conversations on that, but this is a really important mission, I think, to map out the distribution of subsurface ice on the surface of Mars, which is clearly going to be something that's not just scientifically interesting to understanding the climate history of Mars and just the physical structure of that regolith on the surface, but helping us to prepare for human exploration, understanding where the resources might be if we want to take advantage of the resources that are present in situ on the surface of Mars. So I think that'll be big science there. I did want to speak just from a technology perspective in thinking about Mars sample return and the feed forward there as well. In the sense that, not just the obvious things like being able to launch from another planet, like I said earlier, the first time ever to launch from the surface of another planet. So being able to think through how we're going to actually do that. But also thinking through what we call the planetary protection requirements. And so, of course, we have requirements that we're all familiar with of the forward planetary protection, making sure we don't scientifically contaminate the destinations that we go visit, but thinking about bringing things back from Mars. Right now, Mars sample return is categorized as a restricted Earth return, meaning that we have to keep those samples contained until we can determine that they're safe. Well, thinking through that process, how are you going to determine that they're safe? Who's going to determine that they're safe? How do we engage with, for example, the Center for Disease Control and other big agencies within the United States to come to a consensus decision that those samples are safe? And I think it's really important that with Mars sample return, we really are forging that way forward to clear the way for humans to not just go to Mars, but be able to come back, both for the forward planetary protection and backward planetary protection questions. These are big questions. There's a lot of work that still needs to be done there to make sure that we know how we're going to handle even just a few samples of rock, let alone how we're going to get humans there and back. So,
Albert.
There are several things to pick up on in what Laurie introduced there, but the institutional challenges is something that you alluded to, and because Mars Sample Return is a partnership, we're figuring out together, ESA and NASA, how to address a planetary protection question that hasn't been confronted before, and make sure that we do everything we have to do to lay that groundwork, and figure out who really are all the stakeholders, and who gets a say, and it's a cooperation among democratic countries, so we have that advantage. But it also means we have a lot of stakeholders to answer to. We do that willingly and knowingly, but it takes a bit of work. So that's one of the things we're learning. As far as the scientific feed forward things, Trace Gas Orbiter is already based on taking the lead from what was done with Odyssey, is mapping the near surface hydrogen as a lead in then to Ice Mapper coming down the road to know where to look. And I sort of predict, just based on the fact that, for example, Trace Gas Orbiter's neutron detector discovered hydrogen in the near subsurface in Valles Marineris, which is near the equator. That was a bit of a surprise. There are going to be more surprises in the future about where volatiles are located on Mars, and like the story of the methane that you see at the ground and don't see through the atmospheric column, there are going to be some surprises in our understanding. I'll forget to do this if I don't say it now, but one of the things that I remember about all the time, I used to remind myself that Mars really is an alien world. We all know the facts about the atmospheric density and so on, but everybody here probably has seen the pictures of the sunrises and sunsets and the beautiful blue sunsets in a red sky. If you think a little bit about that, that says exactly how alien a planet it is. And we need to remember that. It's not going to be easy, and there's a lot of basic knowledge we need to gain. So the drill, we're going to have to go into the near subsurface in more than one place, probably, to understand the gradient of the oxidation that chewed up the samples for Phoenix. to understand the hard layer that was encountered by the mole on InSight. Just in order, if we want to have humans and build structures on Mars, there's a lot of little details that require a basic scientific understanding of the geotechnical environment, not to mention all the stuff which we don't really, on this panel, aspire to, but it's also basic science. It's all the human physiology basic science that we need to invest in. I get to learn about that because I happen to be in the same directorate as people who do it, but there's a lot of science feed forward. I suppose there's more also from bringing samples back from Phobos.
Yeah, indeed. You know, the concept of going to a place for humans in this exploration zone and be able to use the resources that are there. Water is the critical resource. We know it's in the crust. How deep is it in the crust, and how do you get to it? And so the drills that we've done and we're going to do are going to be really a critical set of information that will enable us to figure out what the best way to get access to water resources. So Masaki, you know, with MMX going to Phobos and Deimos, what new exciting things do you think will happen from those explorations that human exploration can take advantage of?
I might not answer your question because this is something that's been bugging me ever since the last panel I was attending. So yeah, I mentioned about the frequent OK size mission because I believe we all agree that we have to learn more before we send a human to Mars. But when do we find ourselves that we've learned enough? I think that's a really interesting question. But in addition to this kind of science-oriented question, ever since the last the first panel in the morning, I was been thinking that there's another aspect. We're not ready to send human to Mars until we are fully confident. We know we're confident about the synergy with the robotic system, how to work together with the robotic system. Unless we are fully confident about this, maybe we're not ready. And like ChatGPT, at least in the Japanese society, there's a growing anxiety about the robotic system. And unless we overcome that issue on ground, we will not be able to send a human to Mars. That's been bugging me ever since the first panel in the morning. And I'm sorry not answering your question directly, but just wanted to release myself by mentioning this. Yeah.
I appreciate that topic. We can riff with that one for a while.
Yeah, we can. We'll touch on that as we get into some technology discussions. But the concept of going to Phobos and Deimos and really studying them, I think, is incredibly important. I mean, they could be the space station, the future space station of Mars.
Yeah.
And how they fold into future human exploration, you know, is waiting, I think, for your mission to be able to interrogate, look at, understand, and be able then to really assimilate that kind of knowledge. The concept of delivering on a regular basis material in support of the landings, humans landed on the surface. They might be a staging area. They might then drop material using some of the techniques of smaller payloads that we also have to pioneer. You know, as you point out, the concept of having an inflatable is really new. We haven't done that before. That's very important. I mean, we used airbags for the smaller missions like Sojourner, but also Spirit and Opportunity. So new concepts like that are being tested, I think are going to be extremely important, just in the area of delivering supplies.
So let me touch a little bit on MMX. Well, it's a full international collaboration, your contribution from NASA, ESA, France, and Germany, and maybe more into the future. But like Phobos, we started planning this mission thinking that we have some expertise in small body sample return missions. Then what's the interesting target? We came up with the idea of Phobos because that's a small body. We can sample return from it. And at the same time, that's going to be a very nice first step for JAXA to be a member of the Mars Exploration Club. But then Phobos has that kind of human exploration taste. And France and Germany are really providing us with a small rover that will run on the surface of Phobos, maybe jumps a little bit.
If it crawls, we'll be happy.
Yeah, and again, you know, learning about the geotechnical information about Phobos. and from the behavior of the rover, as well as from the samples we get back from Phobos. I think, so it's something we didn't intend at the beginning, but giving the position of Phobos in this human exploration perspective, I think that samples we're getting back from Phobos doesn't only have a planetary science value, but it also has those, I don't know, human exploration driving force as well. Yeah.
Looking at the radiation environment, for instance, I mean, half of the environment is shielded by Phobos itself from cosmic rays. These moons are tidally locked, and so you have a surface of Phobos that's pointing constantly at Mars. And so another huge area of the sky is taken up by Mars itself for cosmic rays. So I would estimate the cosmic ray flux in that area would just drop significantly. But how much? And how can we leverage it? How can we use it? So those are important elements for understanding human exploration, I think, and how those moons might fit in the future.
We do have a radiation monitor on board, yes.
Yes, yeah. Right. So those will be really critical things. Well, we have gone a long way in terms of working with all the agencies together to make missions happen, and some of the agencies do their own thing, of course, based on their programmatics. How do you think, and this is a question for the whole panel, how do you think our international participation and involvement in each of the agency missions will change over time? Have we set a course that's working and we won't change, or is it going to increase or decrease? Lori, what do you think we should be doing?
I'll go first. I mentioned the Mars Ice Mapper a little earlier, and I think that's a really grand new experiment in how to not just, the more traditional way where we, have one agency is the big lead and the others kind of provide small contributions. I think with Ice Mapper, we really do have a case where there's multiple equal partners really trying to forge a way forward. And it's not easy because, of course, all different agencies work on different timescales and have different budgetary challenges at different times. And so it's a real challenge. But I think there's an opportunity there to explore at least one new model for how we collaborate internationally. But I also think that the things we're trying to do are bold, and I think we all benefit from the collaboration. So I think Mars Sample Return is another example where, again, challenges of working together, but again, the ability to do something that's bigger than either agency could do on their own. I think is another wave of the future, being able to leverage the capabilities of the other agencies. I also think that there's opportunities going forward. We kind of alluded to this, and I think Masaki also alluded to it in his, so I'd be interested to hear from the JAXA side. But there's a lot of emerging interest in countries that are smaller, have smaller budgets, but they really want to participate and be part of space exploration. And whether it could be providing hardware, but it doesn't have to be hardware. There's other ways to participate in space exploration. And so looking for opportunities to work with other countries that really want to participate in space exploration and at the level that that they have the ability and where they have their expertise, I think that's going to be, fertile ground as well, looking to expand our community of partners.
I think the Artemis Accords is the start of that.
Absolutely.
And that's not between agencies, it's really between governments.
Exactly.
And so the consequence is that, you've really made a major partnership that you want to be able to start leveraging. So that's all new and open and fertile ground, I think, for future work. Albert, what do you think the international relationships and how that will change from an ESA perspective?
I guess at ESA we're very comfortable with lots of different models of collaboration. So I'm saying, well, what do we need to do that's different or new? But certainly, even within our organization, we have smaller member states, and they're very interested in having opportunities. With less resources than our big member states. The obvious ones: France, Italy, Germany,
right.
Spain, UK. And we're also getting their associate member states who will become member states. So CubeSats at Mars, the OK-sized missions is something ESA is thinking about as well. And there are going to be opportunities there. And certainly there are lots of there are lots of excited people around the world, young people, not in just Europe, North America, and East Asia, who would like to participate to exploration in space. And those opportunities, we need to figure out ways to get people involved as well. And I think we're trying to do that. So that structure of the OK size and regular access, and it's the difficulty is convincing stakeholders to make space for other people.
Yeah.
But it's something that I think everybody recognizes. It's the who goes first issue. So indeed, the model of Ice Mapper is a fun one.
Yeah.
I sort of somewhat equal partners on Mars sample return with just a binary relationship is tough enough to organize. I'm impressed of a 3 or 4-way one on Ice Mapper.
Well, you know, Rosetta had so many countries involved in that. That was such a tremendously successful mission. But you had a lead agency. Now, you know, in the 12 years I was in planetary science, one of the things that we started out working for Trace Gas Orbiter was a 50-50 relationship between ESA and NASA working that, and we had a problem.
Yeah,
that
you let us
ended
down.
that ended up to be too big a bite. We really have to have a lead agency, and that lead agency then works the partnership. So that's what I found out as a critical element in the international relationships. But then the number and who and how to work that. You know, we have a lot to grow in that particular
With
area.
a sort of project manager hat on, an important part of getting progress is somebody needs to be setting the metronome and saying, we're going, and this is what's happening in 3 months, and this is what's happening in 6 months, and we're going to get there. And oh, we missed that, but hey, you guys need to do more work and catch up. And that, if you just wait for somebody in a crowd to make things happen, it might, if you get lucky,
Right.
but you need someone has to be the leader.
Right.
There are different ways to organize the leadership, I think,
Right,
but it's
indeed.
I think it's a truth of how human beings organize ourselves. And even when you get into very, very big projects and organizations, there has to be someone setting that metronome and that clock, and
That's a good point.
pulling things along.
Relative to JAXA, you know, your tremendously successful missions, you lead those missions, everything from GeoTail to MMX, and then partner with many of the other agencies, and that's been a model that's been tremendously successful. Is that going to evolve in many ways, and how do you think that will happen?
But it's nothing of half official, half my personal, thinking. But
Sure.
Well, I was in Umera for the sample return capsule recovery operation of HABSA-2, and I was really struck by how nice Australian people are to us. Because what you do with the HABSA-2 mission is that you import something weird from space, and without opening it, we export it to Japan. And the Australian people let us do this. We didn't even tell what's inside until now. Now that we are.
It's extraterrestrial.
I really thought that I want to be nice to the Australian people, and then I learned that space is really emerging in that country.
Yes, it is.
And then how can we work together? Well, now we're kind of visible because of the big success with the HABSA-2, and we came up to this stage thanks to your help. So we want to be nice to somebody who's emerging now. And then that was really the push behind trying to make our Mars landing program as shareable as possible. So yeah, we are lucky to have our own launcher. But other than that, we're not that different from smaller countries in a sense. But now, luckily, we had the launcher, we had a successful mission, so now we want to be nice to smaller countries, as you have been nice to us. So that's basically the driver behind the Mars landing program we have in our mind.
Well, one of the key aspects of our science programs is on occasion, not always, but on occasion, we end up with technology demonstration activities. For Perseverance, that was Ingenuity, tremendously successful. Who would have thought, right? I mean, there was a lot of naysayers.
Mm-hmm.
Well, what are some of the technology changes that are occurring, and is that moving so rapidly that we can think about having some demonstration technologies that we would launch and do? Lori?
Yeah, so let me I wanted to go back a little bit. Yeah, I'm going to incorporate the technology part of this, but I wanted to go back to, I had mentioned at the beginning that we're in the process of kind of vetting this plan for the Mars exploration program going forward. And one of the key components of that plan is that after Mars sample return, we want to try and establish a sustained budget level, and then at something that we think doesn't have big peaks and valleys in it, but more at a sustained level. And then within that program, have flexibility to have more frequent access to Mars with smaller missions, with more international and commercial partnerships and things. And a key part of that is the technology demonstration and the technology development, because I think with that kind of longer term plan where you can have smaller piece parts that can move around and provide more flexibility, it gives us more of those opportunities to try out new technologies, to look at, for example, swarms of CubeSats, for example, either providing key infrastructure, whether it be communications or imaging, or also doing science in swarm configuration. So I think there's opportunities there. There's opportunities on the surface. There's all kinds of places where we can push technology, and in a program that has more flexibility in it, I think that should give us more opportunities. That's the hope anyway.
Right. So relative to Percy, the concept of MOXIE and the arrangements that were made with Human
Sure.
Exploration and STMD, our technology directorate, those were all really tough to do, but everyone came together and made things happen, and that was so important steps.
Yeah, well, you mentioned that. I mean, with Perseverance, of course, with Mars 2020, there were so many great opportunities to leverage that amazing mission, but to do all these other things as well. So you already mentioned Ingenuity helicopter, which now has 51 flights under its belt. It was only supposed to have 5. It has 51, and still going strong, with no signs of wearing out, which is amazing. You mentioned MOXIE, which was from the human exploration and the technology side of the house, looking to demonstrate the ability to convert the available atmosphere on Mars and turn it into breathable oxygen, or at least that purity of oxygen that would be breathable. We also did things like instrument the entry shield so that we could learn from that and not have to over-design entry systems in the future, to better design, be more efficient in our entry system designs. And then we also did things like for the one of the instruments, Sherlock, I believe, that had the calibration targets that included astronaut spacesuit materials and face shield materials, so that we could see how they degrade over time in the Mars environment and see how they perform. So I think a variety of different experiments that are helping us feed forward.
Yeah, so those are really important ideas and things that we want to keep up with. Technologies. Albert.
Yeah, it's an active part of how we think about exploration at ESA, and there's a whole department that looks at the portfolio of technologies that are necessary across the board. Again, we have the opportunity, because we are in an organizational structure where all of exploration is all together, the human and the robotic, that the technologies that are being looked at are relevant for physiology, they're relevant for self-sustaining space stations, they can be relevant, and it's the same team that has to look at it. It does mean that it's a very wide-ranging portfolio, and it's not always obvious how to tie those things to future implementation. I think but it's important for the agency to be investing in those new developments, and then from the basis of a portfolio to be able to have available a knowledge base of what's possible. I don't know, that technology isn't the hardware. Technology is the people. This is Albert's opinion, but I think it's actually understood in the community. It's how many people you have who know how to do something. That's the investment you need to make. And if you do something once, that doesn't mean, we label it technology readiness level 9, let's go. But if only 3 people know how to do it and they've all retired by the time you actually use it, you have to start over. So knowledge management, knowledge maintenance, innovation, and communication of the understanding. So it's a whole ecology that we all have to participate in and manage. And it's going to be true in spades for pushing human exploration beyond cislunar space. That the people who go, because of the distance, are going to have availability to understand how to fix the machines they take with them. And that's going to take an interaction with those machines that are also going to have to become more autonomous because there will be less humans to operate them. But those humans who operate them better be fantastic programmers, which, by the way, I think is the key to understanding ChatGPT. My colleagues who have the most fun with it are the people who just innately know how to program code because they know how to talk to an AI. And so that's, again, human-machine interface is going to be a big undercurrent of the whole story, I think, of the next few days here in this summit.
So Masaki, there's a number of technologies you guys have pioneered. You know, the small missions, the sample return activities. Are there plans to invest in certain technologies that would feed forward to human exploration?
Yeah, and I'm deflecting your question. I'm sorry, I'm not really answering your question directly, but something that's I'm thinking nowadays is that, like, for example, a CubeSat. When you say CubeSat in old school, people used to think that it's a CubeSat, it's my spacecraft, I can do everything all by myself. But I think that's an old way of thinking. CubeSat is, when you say CubeSat, there are two issues. You have reliability issue and the capability issue. Reliability, you have to improve it. You have to let it work. And you should put all the effort into, elevating reliability. But when it comes to capability, you cannot do anything. It's limited. But then what do you do? Well, each CubeSat has a limited capability. But then how do you leverage its capability? Maybe a swarm of CubeSat, or get assisted by other components, assisted by other systems. So it doesn't have to be a standalone CubeSat. It can function nicely if it's embedded in a larger system or if it's embedded in the swarm. So I think this kind of way of thinking, when you say CubeSat, people try to think that you have to do everything by yourself, but the capability is limited. Then you end up with, your goal is, what you get is limited, but if you think it in a different way.
Right.
Yeah, maybe.
That actually is really important, the
yeah.
concept of things that are working and how you can approach challenges and problems by thinking in different ways and different implementations. So we have a few minutes left. If we have some questions in the audience, now is a great time to come up. Have one question coming up. No, he's going to the bathroom too, just like I did earlier. All right, so, here we are. Yes, ma'am, go ahead. Yeah, it's hard to see. Oh, we have a student.
Why won't you bring samples from the Rosalind Franklin rover back to Earth?
Sorry, can you repeat it one more time, please?
Why will we not bring samples from the Rosalind Franklin rover back to Earth?
Yep. Good job. Here one.
It's taken us a long time to get the Rosalind Franklin rover ready to go to Mars, and bringing the samples back was not part of the planning when it was originally designed. So the rover is built, it's ready to go. Unfortunately, it didn't get launched last year because we were going to launch it on a Russian rocket, and Russia invaded Ukraine, and Europe put in sanctions in place, and we broke our partnership with Russia. So we're now building our own lander to get the rover to the surface. We're not changing the rover to put a whole sample collection system to put the samples into sample tubes the way Perseverance did. It would actually take a bigger rover. It would take a rover about the size of Perseverance, which is about a ton. Rosalind Franklin is 300 kilos, so a bit smaller, size of a golf cart compared to the size of a pickup truck. Nevertheless, we'll bring the data from those samples back, and we have on board a really amazing analytical laboratory for crushing the rocks and studying the rocks. And I'll crow a little bit, since I was the payload manager. But the cooperation between the Germans, the French, and the American contributors to the Mars Organic Molecule Analyzer, plus the other two instruments, the Spanish Raman spectrometer in that analytical lab and the French hyperspectral infrared and visible imager, we've managed in the system and the setup, and we've tested this. It will work. We crush a sample and we'll co-align the instruments on the same sample. Curiosity takes a sample and gives a little bit of it to one instrument and another bit of it to another instrument. We're going to actually have the data all at the same place, so that's something new. And we'll be able to combine that information so we'll know which mineral had the organic molecules on it, not just the average. And the organic molecule analyzer, one of the key features is it has a new method of pulling the organics out of the rocks that hasn't been flown in space before, where we're, instead of just heating the sample, pyrolysis, which is what's been done on Viking and on Curiosity, we have laser desorption. We zap it with a laser. The advantage of that is you don't just boil off the smallest organic molecules, you pull off some of the bigger ones. And we think that the bigger ones are going to be really interesting for understanding whether life got going on Mars.
The bigger, the better. Life makes big organic molecules. Okay. I think do we have time for one quickie?
One quick question.
All right. Yes, sir.
Yeah. The question is really, in one word, China, or in other words, 5 years from now, we have the same panel and there's another chair there. What do you think will be different at that point? What do you think?
5 years.
Okay, I can take a shot at it. We'll be talking science, like we always do. Science has been the undercurrent of everything that these agencies have been doing since the beginning. Even during the Cold War, our interaction with Russia was fantastic. You know, there's wonderful scientists all over the globe. We need that interaction to really make major steps forward, and that's got to happen that way. Okay, Chris, back to you.
Thank you. Wonderful. And great final statement as well. So.